Welcome back to Dan91's Garage. This week we're going to talk about how to tune the DET3 for fuel and ignition timing that we've installed on the Turbo Starlet. So if you haven't watched the previous episodes where I actually wire it into the car, there's a quick install guide and I'll put a link for you up here because all of that stuff leads into what we're going to talk about today and the setup we're going to be going through on the computer later in the video. First off, we'll talk about the map sensors. The Starlet 4E FE comes with a 1-bar map sensor. That means all it can read is atmosphere. It cannot read any boost, and therefore as soon as you turbo the car, it will send 5 volts to the ECU as soon as you start to see boost. And the Toyota ECU has a thing called fuel cut or boost cut, which essentially puts a rev limiter on it, and all of a sudden it will stop your fun as soon as it sees sort of like anything near the 5 volts or as soon as it comes on to boost. So it's no use for tuning, so you have to replace it. Because I'll be running approximately half a bar of boost to start with on this Starlet, the idea was originally to use a glanza map sensor. That's obviously 2 bar, so we have 2 bars in total, 1 for vacuum and 1 for 1 bar of boost. The good thing about the glanza map sensor is it's plug and play to the Toyota Starlet EP91 4E FE loom. You literally unplug the old sensor, plug the new one in, connect up your vac line and it's ready to go. The problem with them is they're getting very rare to find now, and they're quite expensive when you do find them. Originally, the first ones I bought were costing about 35 quid. Nowadays, people are asking perhaps 150. So I decided not to waste my time and effort trying to find one and spend that amount of money on one. It's just the way it goes with car parts that are this old and this rare. As I've got the DET3 Plus, it already has an inbuilt 4-bar map sensor. You pay an extra 50 quid, I think it is, for the DET3 Plus over the DET3, but you get the map sensor you need in the unit itself. It's all hooked up from the previous episode, so what we can do now is we'll jump over to the computer, set it up for the right configuration to use the 4-bar map sensor to run the engine. See you guys in the computer. So we'll start with scales configuration. So analog in on number 1, that's the 1-bar map sensor, and we're going to leave that as a linear voltage scale 0 to 5 volts. Analog in on 2, that's the 4-bar inbuilt map sensor in the DET3, so we need to choose DET3 with built-in 400 kilopascal map sensor. Analog 3 is the analog input from the AEM wideband gauge, so we need to choose AEM wideband AFR scale. And analog 4 doesn't have anything connected to it, so that's just going to be a linear voltage scale 0 to 5 volts. Then we need to save those as whatever particular title you want, so turbo scales or video test scales in this example. And then you need to choose that as default scales, because otherwise every time you fire up the DET3, it will come in with the default scales here that aren't what you want for your particular sensors. So next up, it's ignition configuration. And because we've intercepted the IGT wire going to the ignition module, there are very specific settings detailed in the manual. So ignition mode is retard single signal, ignition input type is Hall effect or optical sensor, maximum RPM should be 100 RPM minimum above the red line of the vehicle. So the Starlet red line's at 6500, so that's 6600 RPM we put in this box. The maximum retard for the ignition in degrees, I don't think we're going to need any more than 20, so that's what I've used there. And the number of signals per 720 degrees or 2 revolutions of the crank on this particular car is 4. So we apply that and click OK. And what that does is it changes the scale here, so it limits us to 6600 RPM. Now we'll look at the setup tables. So in the fuel table, modify is the map sensor signal voltage we will use in the fuel table cells to add and subtract from before sending out the modified signal to the Toyota ECU to adjust the fueling. So we're going to be using the 4-bar map sensor on analog number 2. So that's what we select from the pull down menu here. Load is the map sensor signal we'll be using to move us around this table on this bottom axis. So we obviously want to use analog in on number 2 because that's the 4-bar map sensor that can actually read boost. And you can see here analog in on number 2 is displayed because that's what we've got selected here. At the bottom here, we've got the 2D corrections. We won't actually be using these to control anything. However, I do like to display analog 1 here and analog 3 here, which is the AFRs, so I can at least see what air fuel ratios we've got on this particular scale here while we're working in the other tables at the top. So correction 1, we use analog 1, and correction 2, we use analog 3. So for the ignition table, load again will be analog in on number 2, because that's the 4-bar map sensor that's going to move us around the table on this bottom axis. Correction 1 is analog 1, and correction 2 is analog 3 for the wideband again. Same with the PWM tables. We're not going to be using any of the PWM tables right at this point, but I still like to use load, analog 2, correction 1, analog 1, correction 2, analog 3, and the same for the PWM table too. So next up it's analog inputs. And this is where we size the tables to show as much of the sensor range as we need for the intended boost we'll be running without wasting cells that we'll never travel to, along this bottom axis here. For the half a bar that I'll be running, I've chosen a maximum value of 0.8 bar. And we can see that here for analog input on number 2. So we'll show minus 0.8 bar to plus 0.8 bar on this lower scale down here. This allows us 0.3 bar of extra headroom in case of a slight overboost moment without wasting too much of the 16 by 16 table. We don't need to trim down analog in on number 1. Analog number 3 is for AFRs, so we want to see the full range, and analog 4 doesn't actually have anything on it. If I was worried about going any further beyond this table, I can always set up an overboost warning light through the parametric output function, which is covered in a separate video. Finally, it's analog outputs. So in this first options box, we get to choose the minimum output voltage that will be sent from the DET3 to the Toyota ECU. What I noticed was, if you pull out enough fuel in this table, that the signal voltage on the analog out dips close to about 1 volt. Now, when that's sent to the Toyota ECU, it performed a safety rev cut, almost like a boost cut. But the thing is, if I add fuel to the DET3 table, it doesn't do it. So we'll rev it till it starts conking out. And if we add fuel in the table, it goes away. And if we add fuel, that obviously adds voltage, so we don't dip below our 1 volt again. So I tried this several times and it was repeatable. So it looks like the Toyota ECU has 2 safety limit cuts. The first at 1 volt as its lower limit, and the second at around 5 volts as upper limit. So the analog output minimum I've set to 1.1 volt, which prevents the cutting at the lower level, and the max can stay at 5 volts because we won't be getting there with our particular setup. What you've also got to remember is, the higher the capacity of the map sensor, the lower the voltage is per bar. So I added a blanket 1.25 volts to the entire analog in signal, which gives a better starting point when adding and subtracting fuel in the cells in the fuel table. If you don't do this, you'll find that you don't have to remove much fuel in the naturally aspirated area, but you have to add quite a lot of steps of fuel for when it does come on boost. You can add or subtract 128 steps of fuel in the table cells. Each step is worth a certain voltage, and that is chosen here. I've chosen the middle option, which is 0.098 volts, and that gives you a good mix between a fine enough adjustment to get the AFRs you want without ever running out of the 128 steps that you're permitted to use in each cell. So we apply that and close. So now we'll start to rough in some numbers in the fuel and ignition map. So we'll start with the ignition. So the starting point is to retard the ignition by 1 degree per PSI of boost. So this is where we first start to come into boost. So I've got -1 in there. At the top edge here, it should be -12. So I've gone through and sorted out all of these columns. So when we're in this column, -1, -3, -5, -7, -8, -10, and -12. So that's a good place to start. Now that's assuming you're using stock base timing of 10 degrees before top dead center, which is what the Toyota 4EFE engine is usually set to. If you add an extra 5 degrees to that, so you're 15 degrees before top dead center, You can then take out an extra 5 degrees in the entire table. And now we'll be back to the stock timing of 10 degrees before top dead center. That means that when you're in the naturally aspirated part of the map, you can then release an extra 5 degrees maximum of ignition advance to help improve performance naturally aspirated. So for example, if we enter -3 in there instead, we'll now be 2 degrees advanced over stock to give us a bit more power. So for the fueling, we'll start off with basically the more vacuum and lower load you've got down the bottom end will need less fuel, and the higher the load, the more boost. At the top end, you'll need more fuel. Pretty basic, really. So what I did was I started off, just start the engine, and obviously it'll be going through its cold start enrichment, so there'll be a lot of fuel in there anyway, but after about sort of a minute or two, it will have calmed down a bit, and you just select this bottom corner of the map, which is where you'll be idling. So once you've selected these few cells in the table, then you can just adjust that until the AFR gauge says about 14.7. Again, just do it roughly, get it in the 14 somethings, just so it doesn't soot the plugs up, basically. Then whatever numbers were in there, I just took them right up those columns to the very top for all of the RPM points in that particular set of rows. Basically, before you try and drive it, you're going to have to put some numbers in. This is as simple as that. And I took an absolute shot in the dark and just punted some numbers in, basically. So started off at the sort of leanest end, then went through into the mid-range, and then started adding fuel to the top end. When I put my numbers in, first of all, for my first drive, I didn't have anywhere near enough fuel in the top end for the boost and stuff, but you just sort of back out of it and everything, and then adjust the table to add more fuel. And now it's time to drive and tune each individual fuel cell, and this needs to be done on a closed road. So I turned the narrowband O2 signal off, that way the Toyota ECU can't adjust fueling with short-term and long-term fuel trims, and then you turn the data logging on. So go to the log window, you choose which sensors you want to show up and actually be logged. You don't need all of them going on, so these are the ones I've chosen for this particular logging. And then you click enable log, and that will start logging as soon as you click that button. Then you drive around for a bit, starting with the NA part of the map, which is obviously this area here. Don't get into boost yet, because boost is dangerous, whereas driving around naturally aspirated is a bit safer. So this is the area of the map to drive around in. If at any point you see lean readings on the AFR gauge, or you hear detonation, you need to lift off the throttle and get out of that part of the table. Then you need to stop the car safely, and then you need to adjust the fuel and ignition tables to remove the problem. So once you've done your data logging and you've done some varied driving, sort of uphill, downhill, and collected enough data, what happens is you turn the log off, go back into the fuel table, and then if you click A3 here, what that does is it overlays the AFR readings that were recorded in the data log of the DET3 onto the actual map. So now we know that, for example, obviously this is all 8.5 because we're not driving anywhere, but this might say 8.5, or this might say 14, this will say 12. And then you can adjust the fueling in each cell based on the recorded data log AFRs. So then you click the clear button to erase the current data log, re-enable it, take it for another drive, and then use that data to finish tuning your map. Keep repeating the process until you've done all of the fuel map. The second way of doing it is you can have two people in the car. One person driving, one person operating the laptop. The person operating the laptop is the one that looks at the AFR gauge, and then they make the changes to this map to increase or decrease the fuel. So what I was tuning for was on cruise and light load, I was aiming for around 14.7 AFR. Then obviously this area here is where we start to go from naturally aspirated into boost. So I wanted this area here to drop down to perhaps 13, low 13s. Then as we came onto boost, I wanted it to be around 12 AFR. So that way it's nice and rich, nice and safe, keeps things a bit cool in the combustion chambers. Now what you've got to remember is when you're driving around on your closed road, you won't get to all of the places on this map. Now, it's unlikely you'll get to sort of like very high vacuum and very high RPM, just like it's very unlikely you'll get to, you know, sort of 7.5 PSI of boost at idle. So these, the areas of the map here and these sort of areas of the maps here are going to be very difficult to actually get to. So this is why you need to do things on a dyno. So what they can do on the dyno is lock the road speed so the engine stays at a certain RPM. So we'll be staying in this row, and then using the throttle, they can obviously travel from this end of it all the way up through these cells, visiting every cell. Obviously, depending on the engine and the turbo size you're using, you may not actually be able to get to certain cells in this map because you may not even be able to produce that amount of boost at a specified RPM. Like, it's doubtful you'll get 7.5 psi at sort of like 1200 RPM. So this area of the map is always going to be kind of unvisited, but it's good to have numbers in there, because if you've got 0 in there, you won't be adding any fuel. So always remember that as well. And last up, it's the ignition tuning. So to get the most power out of the engine, you'll need to have the ignition timing adjusted to what is known as minimum best timing. This is where the spark is timed to produce the maximum torque for the combustion event. Most engines on pump fuel will be knock limited, meaning that the engine will suffer detonation before reaching minimum best timing. So when trying to reach MBT or knock threshold of a particular car, it needs to be safely monitored on a dyno with a knock detector or with DET cans by a professional adjusting the tuning. When knock threshold or maximum torque is reached, which will be shown by the torque readout of the dyno, the timing is then retarded by a few degrees to have a safety margin. Trying to do this on the road or on a closed road just simply isn't possible. So that's it for this week. Thanks ever so much for watching, boys and girls. Hopefully this has given you an insight into how I tuned my car on the DET 3. Now I've finally got the fueling and the ignition sorted conservatively, I can actually go out there and enjoy the car. It's been a year to build it so far and film this stuff for you on YouTube. I hope you've enjoyed the series. It's certainly by no means over, but at least I get to go out and drive the car now. So take care of yourselves, and I'll see you soon.